Let's work some Coulombs law problems. Now remember, Coulombs law tells me if I have two charges and say they're negative and they're separated by some distance, d, let me get my pen working here, and they each have a different charge. So say this one is Q1, this one is Q2, and they're separated by some distance. Oh, let's use R. Then the electrostatic force between them is going to equal K times the charge on the first times the charge on the second divided by R squared, where K is Coulomb's constant, which is 9 times 10 to the 9th Newton meter squared per Coulomb squared. That's a 9. So it's 9 times 10 to the 9th. Now, in your calculator, a lot of times you can put in 9 and use your EE button, 9. So a lot of times in class I say it's 99. Now, there's another part of these problems. Whenever you're computing the force, don't take into account the sign of the charges. So you see I wouldn't put in the negative signs there. However, let's look at what direction the force of 1 on 2 is. 1 is sitting here, it's negative, and it's going to push 2 away. So the force of 1 on 2 is actually to the right. Similarly, the force of 2 on 1, they're repelling each other, so it's going to push it to the left. What if we had two positive charges? Now remember, it turns out it doesn't matter whether they're negative charges or positive charges. If this is Q1 and this is Q2, then Q1 is going to push Q2 this way, so the force of 1 on 2 is to the right, and similarly the force of 2 on 1 is to the left. Finally, if they're both, if they're different charges, so you have one positive, one negative, what happens? Your force is going to be attractive. So when you get the force, didn't do that, the force of 2 on 1, this charge is going to pull the positive charge to the right. Similarly, the force of 1 on 2 is back to the left. You need to be able to draw these. You need to be able to do analysis of these problems. So suppose you have a standard where you have Q1 and Q2 and they're separated by a distance d, and there's a force associated with it. What new force occurs if Q is doubled? Remember, F is K Q1 Q2 over R squared. So if I were to double Q2, I would wind up doubling the force. What if Q1 and Q2 are cut in half? Well, just write your formula out. K Q1 Q2 over R squared. Now Q1 is cut in half, so I'm going to put a 1/2 here. Q2 is cut in half. 1/2 times 1/2 gives me 1/4 of the original force. However, what if D is tripled? Write out your formula. F is K Q1 Q2 divided by R squared. If D or R, you know me, I'll flip back and forth between the two. If it is tripled, it's going to be 1/3 squared, or 1/9, the original force. What if D is cut in half? Well, F is K Q1 Q2, keys aren't working, divided by R squared. If D is cut in half, let's see what happens. This becomes 1/2 squared. Well, 1 divided by 1/2 squared is 1 divided by 1/4, which is 4. Now these become a little bit more complicated. What if Q1 is tripled and D is doubled? Just write your formula. F is K Q1 Q2 divided by R squared. Let's see. Q1 is tripled, so I'm going to put a 3 here. And D is doubled, so it's going to be 2 squared. So this is 3 divided by 2 squared, or 3/4, the original force. What if we're just calculating the force on the particle? I have a positive charge and a negative charge, and each have magnitude 1.5 times 10 to the negative 5 coulombs. So Q1 is equal to 2Q is equal to 1.5 times 10 to the negative 5 coulombs. Now, you can write these separately, that's fine. And their distance is 15 centimeters. Well, immediately you're going to convert that to meters because you know I'm trying to trick you. Calculate the force. F is K Q1 Q2 divided by R squared, which is 9 times 10 to the 9th. Q1 and Q2 are the same, so I can square this. Times 10 to the negative 5 squared. If they were different, I just list them differently. Divided by 0.15 squared. And I get a very nice answer of 90 newtons. Now, is it attractive or repulsive? Well, let's see. One's positive and one's negative. I need to put H on there. So because opposites attract, because it has to be attractive. Had they both been positive or both been negative, it would have been a repulsive force. Now I have two negative charges of negative 3 microcoulombs. Okay, so, whoa, it's not wanting to write. Q1 is equal to Q2 is equal to negative 3 times 10 to the negative 6 coulombs. You need to be able to do that conversion. That's a micro, and it means 10 to the negative 6. And it has a repulsive force of 2 newtons. Now remember, don't worry about the signs. Just we'll look for the magnitudes here. Calculate the distance that separates them. Well, F is K Q1 Q2 divided by R squared. I'm going to solve this for R. So R is the square root of K Q1 Q2 divided by F. Now put your numbers in. R is the square root of 9 times 10 to the 9th times, now I'm going to leave the negative sign out, 3 times 10 to the negative 6, 3 times 10 to the negative 6, divided by the force, which is 2 newtons. When I do my calculations, I see I get a very simple 0.201 meters.